Agile Learning Hub welcomes you all. Now in today's episode, we are going to study an introductory idea about elasticity. This is for the undergraduate first year level, and therefore this will be more basic, some definitions, some parameters and different types of elastic moduli. All these things could be explained in this episode. Now you see this figure. We have a body there, and in the body you mark 2 points and you measure the distance between the 2 points. Now you apply an external force on the body. If there will be any change in the distance between the body, we don't call it to be a rigid body. But on the other hand, if the distance remains the same, even if you apply the external force, then you call it to be the rigid body. Therefore, the distance between any 2 points remain unchanged. When an external force is applied on your body, then you call the body as the rigid body. But on the other hand, you see these examples that I have shown here. In figure A, you have a rubber band which you have already seen. The rubber band will have a length. Now you are pulling the rubber band on both sides. Now what happens? Automatically the length of the rubber band increases. In the second example, you see the balloon. When you blow air into the balloon, the size of the balloon increases. And you see the third example. There you are having a block. In that block you apply a tangential force in the top of the block, and you see it becomes a trapezoid. The shape of the body changes. So in all the 3 examples that I have stated here, either the length changes or the size changes or the shape changes when you apply a force from outside. The outside force you call it to be the deforming forces, because the form of the body changes. Therefore the force that we have applied is called deforming forces. So when you apply a deforming force on certain body, the body is said to be strained. When I say strained, either the length or the size or the shape changes, and therefore we say the body is said to be strained. Now if you remove the deforming forces once again, that is, if you take the first case of the rubber band, if you remove the force that you are applying, it will regain its original length. Similarly, if you remove the air from the balloon, automatically it regains the original shape. Similarly, if you take that block, if you remove it, the body will be once again in the original size. Therefore, we come to the conclusion that when the deforming forces are removed, the body regains its original length or original size or original shape. You call this phenomena as elasticity. Now here, when you are applying an external force on the body, what happens? The interatomic distance between the 2 bonds will be stretched. Therefore, what happens? There exists an internal force inside the body to retain or regain its original position. The restoring force should be equal to the external force that we had given from the outside. The restoring force per unit area set up in the body is called stress. That is, stress will be equal to F by A, where F is the force and A is the area in which the force is acting. And the unit is Newton meter minus 2. And now here I told another parameter is strain. What is strain? I have given 3 examples. You see the figure A. In the figure A, you can see a pipe and you are pulling it on both sides. The length of the body increases. If capital L be the L0 be the original length, then delta L be the increase in the length, then the ratio of the increase in the length or the change of length to the original length is called the linear strain. Therefore, change in the dimension to the original dimension is called the strain. In the first case, it is a linear strain because the length changes. In the second case of the balloon, there will be a change of volume. Let delta V be the change in the volume. The original volume is V0. The ratio between the change of volume to the original volume, we call it to be the bulk strain. And in the case of the shearing strain, there will be a lateral displacement. There will be a change in the length, delta x, in the topmost side, and original length is L0. Therefore, delta x divided by L0, we call it to be the shearing strain. Therefore, three types of strains are available here. Now let us study the relation between the stress and the strain. There is a diagram. You apply the stress. When you apply the strains, automatically there will be a strain. What is the relation that exists between the stress and the strain? As the stress increases, automatically the strain will also increase. That is from the graph. You can see from the graph, from O to H, the graph shows a linearity. Therefore, the stress should be directly proportional to the strain produced in it. And you see the graph, you can go up to the point E. So up to the point E, stress should be directly proportional to the strain, and if we remove the stress, automatically the body will regain its original position, and this region you call it to be the elastic region. After E, the curve is non-linear. So from E to P, the body will not regain its original shape or size or length after the deforming of the deforming forces have been removed. Therefore, we call that distance as the transition side, and that will be plastic in the side. Therefore, this is what we call it to be plastic region. And after P also, this is in the plastic region or plastic deformation starts. The body won't recover its original shape or size even if the stress is removed. And you take the point D. At the point D, the body will break down, and therefore that point you call it to be the fracture point or the breaking point. So this is the relation that exists between the stress and the strain. So Hooke had found out a relation for the stress and strain relation, and that law is called the Hooke's law. It states that within the elastic limit, that is before the non-linear portion starts, that is in the linear portion, the stress is directly proportional to the strain produced in it. Therefore, stress is proportional to strain. Therefore, that you can take the proportionality and put a constant, and that constant you call it to be the modulus of elasticity. E we have represented by the letter E. Therefore, E will be equal to stress by strain. Therefore, this is what you call it to be the Hooke's law. Now, let me explain certain properties of the materials. In engineering, materials that deform elastically are used to carry the loads. You might have seen the bridges. You might have seen the buildings. In the buildings also you have the beams. In the bridge, you have the very large bridge supported by the two beams. And for this engineering purpose, all these bodies could have been used, and we call it as the elastic bodies. Beam is an elastic body, the bridge is an elastic body. Therefore, the steel beam is also an elastic body. The steel is more elastic than rubber, and that's why, which may be very peculiar to us. We may think that rubber is elastic, but rubber is not elastic. Which is more elastic? Steel is more elastic. That's why we are using it for the engineering purpose and for the construction purpose, and that is shown in the figure here. And the second one is, we have already studied that Young's modulus will be equal to stress by strain. If the strain is very small, then Young's modulus will be very high. That means large stress must be needed to produce a small strain. And this is what we call it to be the stiffness of the material. Therefore, Young's modulus is a measure of elastic stiffness of the material. The large value of stress is needed to produce a small strain. Therefore, these materials will be very stiff. Stiff materials, glass is one of the examples. But that won't be very ductile. It will not be ductile. But in the case of the fabrication, materials that deform plastically could be used, which can withstand before the fracture. Say for example wire. Wires are metals. Metals are more ductile. Therefore we can deform it plastically. So in fabrication we have used the materials that deform plastically, and this is called the ductile materials. Brittle, a substance that fractures immediately after elastic stage, is called the brittle material. They won't be non-ductile, example ceramics and glass. So these are some of the examples of material properties. Now here another certain parameters that we are going to study here will be elastic after effect. I told here, when you apply a deforming force, either the length or the size or the shape changes. When you remove the deforming force, it will regain its original position. Now, between the removal of the deforming forces and the recovery of the object, there will be a time gap. That time gap, we can call it to be the elastic after effect. The glass fiber takes hours to return to its original state, whereas quartz or phosphor bronze materials returns very quickly. So that's why phosphor bronze metal or quartz material is used in the construction of the galvanometer wire to suspend the beam. Therefore, this is what we call it to be the elastic after effect. And another property is elastic fatigue. It is the property due to which the elastic body becomes less elastic under the action of repeated alternating deforming forces. You see, bridges have been constructed. Bridge is an elastic body. When the buses are going or the vehicles are going, we are applying a deforming force to the bridge. So there will be an elongation or compression, whatever be that one, that will be taking place. When the bus crosses the bridge, it regains its original shape. So this is repeatedly years and years together. After a long usage of the years, the bridge won't be very useful because it will be less elastic by the application of the deforming forces, and this is what we call it to be the elastic fatigue. Therefore, these are certain parameters that we have studied, and also I have told in the beginning we have three types of changes or the strain produced in the body. Accordingly, we have three modulus of elasticity. First one is the Young's modulus of elasticity. It is defined as the ratio of the normal stress to the linear strain produced in the body within the elastic limit. That means, imagine you are having a wire or whatever it is, you are having a rubber band, whatever it is. I have given an example. I have shown a body. That body is having the length L0. Now, I am pulling it on both sides. When I am pulling it on both sides, there will be an increase in the length. That increase in the length is shown in the figure delta L. Another figure in B, we are compressing on both sides. There will be a compression of length delta L. And that is the strain produced. Therefore, the strain produced, linear strain produced, will be equal to delta L divided by L0 is the original length. That is the linear strain produced in the body. And the linear stress is force per unit area. Force that I have applied, if you are applying a mass of m kilogram, then force will be equal to mg. Area, since it is a circle, that will be pi r square. Therefore, linear stress will be equal to mg divided by pi r square. Therefore, Young's modulus will be equal to mg pi r square divided by delta L by L0. So, you will have this formula mg L0 pi r square into delta L. The large value of E means it resists elastic deformation. Therefore, a large stress is needed to produce a small strain. That's why I have told that steel is elastic modulus of steel is greater than rubber. Now the second modulus is bulk modulus. The ratio of the normal stress to the bulk strain produced in a body within the elastic limit is called the bulk modulus. Therefore, the bulk stress will be equal to F by A, or it can also be equal to the pressure that you are applying from outside. And bulk strain will be equal to delta V by V. Therefore, bulk modulus will be equal to PV divided by delta V. It is represented by the letter capital K. And the third modulus is rigidity modulus. It is the ratio of the tangential stress to the shearing strain produced in the body within the elastic limit. The stress that we have applied is F by A, and the shearing strain is delta X is the change in the upper side, divided by L0 is the original length. Therefore, rigidity modulus represented by the letter L, N will be equal to FL0 divided by A into delta X. And another parameter that we have to study here is the Poissons ratio. That is, when you have the rubber band will have its length L0, original length, and when we are pulling it down, there will be an increase in the length. Increase in the length is delta L, that is L minus L0 is delta L, and you call it to be the linear strain. But at the same time, what happens here will be the breadth will be shrinking. There will be a lateral strain also. That lateral strain will be equal to D minus D0 by D0, and this is called the lateral strain. The ratio of the lateral strain to the linear strain is called the Poissons ratio. For the Poissons ratio of the materials will be varying from 0.5 to 1, and this is about the Poissons ratio. So my dear students, hope that you would have studied a little bit about little fundamentals about the elastic moduli. Thank you.
இந்த வீடியோ உங்களுக்கு பிடிச்சிருந்ததுன்னா லைக் பண்ணுங்கள், ஷேர் பண்ணுங்கள், கமெண்ட் பண்ணுங்கள். இதே மாதிரி இன்னும் நிறைய வீடியோஸ் பார்க்கணுன்னா மறக்காமல் டார்ஜில் லேர்னிங் ஹப்பை சப்ஸ்கிரைப் பண்ணுங்கள். அந்த பெல் ஐக்கானையும் ப்ரெஸ் பண்ணுங்கள்.